Hi, welcome to my Lab 3. The purpose of this lab is to use Newton's second law and the law of gravitational force to find the mass of a black hole given its position, the star mass, and the time step. By using the given amount of data, which is the mass of a star, the time step, which is the number of seconds within a day, and the position of the black hole, we can calculate the mass of the black hole, which was found to be 4.38 e to the 31 kilograms. And this was verified through WebAssign, as you can see. The laws that were used was Newton's second law and the gravitational force law. The second law states that the F net is equal to the sum of F parallel and F perpendicular. And through use of substitution, we can derive the final formula, which was dP over dt equals to d magnitude of p over dt times p hat, plus the magnitude of momentum times dP dt. We can use this and also the gravitational force, which was F equals to g times mass 1 times mass 2 over r squared to find our mass of the black hole. M1 and M2 is the mass of the star and the mass of the black hole. G is a constant, r squared is the radius of the black hole. And given the star's position, which were all these data, this data was calculated for each day for 3 years. And by using the star's data, we can create a Python code to determine the mass of the black hole. And in my code, I created a sphere to represent the black hole. And to save time, I will scroll this and you can look at the code that I have written. The important note to point out is that what I've shown in the PowerPoint is exactly the same as what I put in the code. For example, F net equals dP over dt. And when I run this code, I get this model. The yellow arrow represents the net force, and it always points in the direction of the black hole. The blue arrow represents the force that is perpendicular to the net force and points to the direction of the change in momentum. And the black arrow represents the force that is parallel to the net force and is always pointing in the motion of the changing magnitude. We can observe momentum of the object by looking at position and the time. What does it mean? How is F net parallel, F net perpendicular, and F net different from change in momentum over change in time, change in momentum over change in time parallel, and perpendicular respectively? As you can see, when I run this code, the values are equal. F net is equal to delta P over delta T, and parallel is equal to delta P over delta T parallel, and so on and so on. So if their values is equal, then how are they different? The interpretation is different. Although the equation specifically states that F net is equal to the change in momentum over change in time, it's actually F net is the cause and the change in momentum and change in time is the effect. So basically, like we said before, we can observe the momentum of the object by looking at the position and the time. However, for the net force, we cannot observe it, only its effect. This is because force is an invisible concept, while we can visibly see something's momentum changing over time. The what if question. I'm not going to read this out, but you can take a look at it. Because the gravitational force law, if the motion of the star is the same, and that means that the position of the object is also the same, this is because the velocity of the object is the same going around the black hole, which is in the same position as it originally was. Thus, if the motion of the object is the same along with the position, then the net force acting on the object must be the same. If the net force must be the same, then mass 1 times mass 2 must also be the same. So if the black hole's mass is different, then the star's mass must also be different to account for the same value of net force. Therefore, if the star's motion does not change, then the mass of the black hole can't either. Thank you for watching. This is my lab. Bye.